So this is section 1.4. We'll be working on functions a little bit more. So functions are crucial to math modeling, and therefore we devote a significant amount of time to studying functions in the mathematical fields. So here we go. Let's do a little bit more on functions. So once again, x is your input value, y is your output value, f is your function or your rule that relates x and y. So the value of y is completely dependent on your choice of x. For this reason, we often call x the independent variable, sometimes called the argument of f, and y is called the dependent variable. So let's just do a couple of these. So A says, what is f of -1? So what you would do there is you would replace x with -1, and you would simplify. So this would be -1 minus 3 plus 4. So that's -4 plus 4. So that would be 0. So for part A, you're just going to substitute the number given for your x value, and you're going to simplify. All right. Now, for part B, if you're asked to find f of 2x, you're going to put 2x in for every x. Every time you see an x, you're going to put a 2x. And then we're going to simplify this. And you're going to combine like terms if possible. So there aren't any like terms here. So you would just leave it at that. Let's just go ahead and do that next one on part B as well, just to make sure we're clear on that. All right, so it says 2 times f of x. 2 times f of x. All right, so you're going to put a 2 in front of your function f of x. So that means you're going to multiply. So we got to distribute all this. All right, so I've got -2x squared plus 6x plus 8. All right, so that's how you do B. Now, for C, let's erase some of this so we have some more room here. All right, so for C, let's do the first one. So if we're trying to find f of x plus 2, that means x plus 2 is going to go in where you've got your x, and then it's squared. And then here you've got an x, so we're going to put an x plus 2. All right, so remember when you have a little 2 right here and you're squaring a binomial, you got to double distribute. So I'm going to write it twice so you're not going to make the mistake of just squaring this and squaring this and calling it x squared plus 4. Believe it or not, that is a common mistake. But when you square a binomial, it's double distributing. So I'm just going to continue out here. All right, so I'm going to double distribute, then I'll apply the negative. All right, so plus 3x plus 10 over there. So this is -x squared minus 4x plus, minus 4 plus 3x plus 10. All right, so let's check it. So I applied the minus. All right, there's 2 of those, so that's 4x. Applied the minus. Applied the minus here. Okay, so everything looks fine. So combining like terms for the last step. So we should get this. Okay? Double distributing. All right, so let's see if we need to do any more of these, just to make sure you understand the notation. Let's get rid of that. So if we're looking at part C, the one that says f of x plus 2, so we're just going to take the function f of x, oops, and we're going to add 2 to that. That's all that means. Just simplify that and you'll get that. Alright, so that's this part here. I might as well do the other one just to make sure that you understand what's being asked of you. So for this one here, we're going to take f of x and we're going to add to it f of 2. Okay, so f of 2 means I've got to put a 2 in there wherever I have an x, and this is just going to be a numerical value then. Okay, so what we've got here is f of x plus f of 2. So this is minus 4 plus 6 plus 4, so this is just 6. So I've got minus x squared plus 3x plus 10. Alright, so last one, oops, got rid of everything, erase ink. Okay, so the last one says solve for f of x, solve f of x equals 4. Okay, so here's f of x equals 4, it says. Alright, so let's see if we can simplify this a little bit. Okay, so we've got minus x squared plus 3x equals 0. Alright, let's divide everything by negative 1 to get that leading 1 out of there, and then we'll factor. Okay, so when we're solving these quadratics like this, you can just go ahead and factor them. Of course, you could always use a quadratic formula, but in this case, the factoring is going to be quicker. Alright, so to get a true statement, either this factor would have to be 0, or this factor would have to be 0. Alright, so if x is 0, then we've got 0 times negative 3, that's equal to 0. So this is one of your solutions, makes a true statement. Then on the other one, x would have to be equal to 3. So when x is 3, 3 times 3 minus 3, this part here is 0. 3 times 0 is 0. So this makes a true statement. So when we solve this, we got two solutions. X is equal to 0 and x is equal to 3. And that you would expect if you're solving a quadratic. You can get at the most 2 solutions, but you could get one repeat solution, or you can get no solution, no real solutions if you end up with complex answers. But right now we're working with some real numbers. So now we're going to talk about whether or not we need to restrict what x values belong in our domain. Okay, each of these 6 examples has something specific that we're going to need to look for. So let's take it to a slide that has more room. Okay, so this g of x equals root 4 minus 3x is an even root. Okay, so what an even root is a square root, a fourth root, a sixth root, etc. Okay, so you recall from our prior studies that if you have a negative number under a root, this is really an imaginary number. So this is an imaginary number, so it's non-real. Okay, so we're going to restrict x values only real. Only real. Alright, so if we're only real, that means that the underneath part of the radical has to be either positive or 0 under the radical. All right, so those are the restrictions we have for when we have an even root, positive or zero under the radical. So in our case, 4 minus 3x has got to be positive or equal to 0. Okay, so we're going to solve this inequality. So negative 3x is greater than or equal to negative 4. Divide by negative 3. X is less than or equal to 4/3. Okay, so this is our domain restriction here. X has got to be less than or equal to 4/3 in order to maintain this condition. So on a number line, 4/3, we can be equal to 4/3, or we can be less than 4/3. In interval notation, we would write it domain is negative infinity to 4/3, including 4/3. All right, so this would be our domain in this problem. Let's try another one. Okay, so this is an odd function. So an odd, I should say radical. So a cube root, a fifth root, etc., seventh root, those are odd radicals. Now recall that negative 2 times negative 2 times negative 2 times negative 2 times negative 2 is equal to negative 32, which means that the fifth root of negative 32 is equal to negative 2. So you can have the fifth root of a negative number. It'll also be negative. Okay, so there's no restrictions for odd radicals. Okay, meaning you can be either 0, positive, or negative. Okay, so that means our domain is going to be all real numbers if we have no restrictions. So this is our domain. Let's try another one. All right, so on this problem right here, the issues are going to be 0 in the denominator here, and then a 0 in the entire denominator here. So we've got to explore which x values are going to cause those zeros to occur in the denominator. All right, so your function is undefined when you have a 0 in a denominator. Okay, so we got to restrict our domain. We cannot have those x values that cause zeros in the denominator. All right, so let's try the green part first. So when is x minus 3 going to be 0? All right, so x is equal to 3 would cause a 0 in that green part. All right, so we're going to say x cannot be 3. All right, then let's look at the red part. 1 minus 4x over x minus 3. When is that 0? All right, so let's solve this. We're going to clear the denominator here by multiplying through by x minus 3 everywhere. Multiplying through by the same number in an equality does not change the equality. So I've got 1 times x minus 3. Okay, these cancel out, which was our objective. So that's minus 4x. And then I've got 0 times x minus 3, which is 0. X minus 4x is negative 3x. So negative 3x is equal to 3. So x
is equal to -1. Okay, so x cannot be -1, or you're going to end up with a 0 in the red part, the larger fraction. So let's look at what that would look like on the number line, so we can write it in interval notation. Okay, so it can't be those two numbers, so empty circle. Okay, but it could be over here, here, and here. So that's a three-piece domain. All right, so we've got -infinity to -1 is okay. -1 to 3 is okay. 3 to infinity is okay. All right, so this is our domain for this function here. All right, let's try another one. All right, in this one, we've got several problems. We've got a divide by 0 error potential there, and we've got a problem with an even root could potentially have a negative under the radical. So there's two sources of domain restrictions in this particular function. All right, so let's investigate. So let's try the radical first. So even radical, or even root. Radical and root I tend to use interchangeably. So 2x plus 1 has got to be equal to 0 or positive. So that means 2x is greater than or equal to -1. X is greater than or equal to -1/2. All right? That's for the even root. Then on the bottom, we could have a 0 in the denominator, leading to undefined. Right? So that means that x squared minus 1, what causes that to be 0? Let's just solve it. Square root. All right, so when x is either plus or minus 1, we've got a problem, a 0 in the denominator. All right, so we can't have x being positive or -1. All right, let's put all this on the number line and see how we can indicate that using interval notation. All right, so -1, so that's a no, empty circle. +1, that's a no, empty circle. -1/2, -1/2. It can be that. I've got that little line here, so that's okay to be -1/2. All right, but then we've got this equality symbol here, inequality symbol. So this says x has got to be greater than or equal to -1/2. Okay, so only on this side. Okay, so that red part indicates where we can be. All right, so in order to write that as a domain in interval notation, we're going to say square bracket, -1/2 to 1, round bracket because 1 is not in the domain, and then picking up on the other side of 1, 1 to infinity. All right, so this is our domain in interval notation, considering our restrictions here. All right, next one. So here, let's see what the problem area is. Okay, so we have a denominator here. So in the denominator, we could potentially have a 0. Okay, so we've got a undefined when denominator is 0. Okay, so we got to restrict to non-zero. So that means 6 minus t plus 3. What causes it to be 0? We want to figure it out. All right, so we've got minus t plus 3 root, -6. All right, so let's square both sides. So that's negative times a negative is a positive. So we've got t plus 3 is equal to 36. T is equal to 33. Okay? So t cannot be 33, or you get a 0 in the denominator. Let's check. 33 plus 3 is 36. Square root of 36 is 6. 6 minus 6 is 0. All right? Now, let's not forget that we also have an even root. All right? So let's see. Right there. All right? So we've got an even root as well. So let's check for that. All right, so even root. Okay, so an even root has to be positive or 0. So that means t plus 3 must be positive or 0. All right? So that means t is greater than or equal to negative 3. All right, so if t is greater than or equal to negative 3, then you're going to stay positive or 0 under the radical. So if I put that all in the number line, that'll help us to draw our intervals. Okay, so it can't be 33, so this is an empty circle. And it's got to be greater than or equal. Equal means filled in. Greater than or equal to negative 3. So this side of negative 3. All right. So our domain is going to be square bracket negative 3 all the way to 33, round bracket. And pick up on the other side of 33 going to infinity. Okay, so this is our domain for this function, considering our restrictions. All right. Let's see what else. One more. Okay, so in this case, our potential problem is a divide by 0 error in the denominator. Undefined when denominator is 0. All right, so x cannot be 0. That one's pretty easy to see. Now, the common mistake here in this type of an example is canceling before you identify the problems. Okay, so if you cancel that x out of the denominator, you've masked your domain restriction. Okay, so do not cancel until you've identified the domain restriction. Okay, so this right there, we got a problem. So x cannot be 0. All right, so on the number line, what that would look like is just at 0, you've got a hole. Everything else is okay. So domain negative infinity to 0, 0 to infinity. Okay, so that's your domain. All right, that's the end of those examples. Okay, let's take a look at this function. This is what we call a piecewise function. And what this means is that this function within this curly bracket here is x squared if x is less than or equal to negative 1. So at negative 1 here, it's a quadratic facing upwards. So you've got this graph here, this piece of it that resides to the left of negative 1. Okay? If x is between negative 1 and 1, then you're on this graph here, which is the upper portion of a circle centered at the origin with the radius of 1, and you haven't learned that yet. That's coming in the conic section, but that's this graph here. Okay? And then if you're greater than 1, you're just simply f of x is equal to x, or y is equal to x, which is a line with the slope 1 over 1. Okay, so that's this kind of a line right here. And that resides when x is greater than 1. That one rules. Okay, so notice that the transition places of -1 and +1, you've only got one filled in dot. Okay, the filled in dot at -1 goes with the x squared function. See, it's right there because of this little line here. Now when you get to 1, the filled in dot is on this line of f of x, and it goes with this function here. So the filled in dot is on this part of the curve. And over here, when you get to this part of the curve, 1 is not in the domain of this piece of the curve here. Okay, so this is what we have here. All right, so if I'm trying to find a f of 4, I'm going to plug 4 into the part of the function where 4 is the domain. So looking at here, 4 is over here, so I need to use this piece of the function. So x is greater than 1, that's where 4 is. So I'm going to plug 4 in for x. So that just gives me 4. All right. So b says f of -3. Okay, so that puts me over here. I got to use this part where x is less than or equal to -1. So I've got to put -3 in here and square it according to this, and I'm going to get 9. Okay, so that's b. Now, c says, what is f of 1? Okay, so over here, we've already talked about that. F of 1 is this filled in dot there, so f of 1 would be 0. Okay, so when x is equal to 1, you've got to put 1 in here. 1 minus 1 squared is 0. Square root of 0 is 0. All right, d, what is f of 0? Okay, so that means we're on this curve here. 0 is in this part of the domain. So if I plug 0 in here, I've got 1 minus 0 squared. That's 1 minus 0, so that's 1. Square root of 1 is 1. Okay? Now we're only using the positive part because these are functions. There's no plus or minus written in front of there, like that. Okay, so you're taking the positive square root. All right, e, it says f of -1. Well, we talked about that already. This is your filled in dot. So when x is -1, you're looking at this little line here. This part of your function is where we want to plug it in. So -1 squared is 1. All right, so then we've got f here, -0.999, so that's slightly to the right of -1. Okay, so I would have to plug that into this function here because I haven't gotten all the way to -1. So the indication, the point of this, giving you this kind of a number, is that you're going to recognize you're over here and not over here. Okay, so we haven't gotten to -1 yet. So we're in this part right here. We're in here. So I got to plug that into my calculator. Okay, so I did that, and I got 0.0447. Okay, so that's how to determine f of x when you're dealing with a piecewise function. You've got to be very careful that you're on the right piece of the function when you plug in the number. Okay, so this is a good example of a modeling problem, an application problem. So we need to understand how these functions work. And these are going to come up a lot when you get into calculus as well. So in this problem, it says the height h in feet of a model rocket above the ground in t seconds after liftoff is given by this function here. So it's governed by this upside down parabola function. See, negative in the front, squared term, degree 2 term. So this is a upside down parabola. if time is between 0 and 20 seconds. All right, and h of t, the height of the rocket, is 0 if t is greater than 20. So that must mean it's on the ground, t and thereafter. Okay, so we're asked to find and interpret h at 10 seconds and h at 60 seconds. All right. So what I've done here is I've graphed this upside down parabola, and when t is 0, if I plug in 0 in here, this term goes to 0, this term goes to 0. So that must mean when it starts. That's your liftoff time here. T is equal to 0. Having a negative time doesn't make any sense in a problem such as this, in a rocket problem or a projectile problem. Okay, so if I plug in 20 into this function and I try that over here, I can see that it goes down to 0 again. So that must mean it peaks out right here and then hits the ground over here. So remember, parabolas are always symmetric. Okay, so that means that halfway in between 0 and 20, which would be 10, would be where it hits the peak. All right, so they have an axis of symmetry. All right, this right here is your axis of symmetry. Okay, so what's going on here at h of 10 is that you're hitting your max. All right, and then it wants you to interpret, what happens when h is 60. Okay, so over here, you're way out here when h is 60, so you're on the ground. So you're on the ground. You've landed 40 seconds ago. All right, so that's kind of a meaningless question, but we interpreted it. All right, and then it says solve h of t equals 375. And so that means that there must be some time in here where the height is 375. Let's see if we can figure that out. All right, so that must mean I'm in between 0 and 20 somewhere, if this makes any sense. So let's say minus 5t squared plus 100t somewhere equals 375. So we're going to solve this quadratic. All right, so we're going to divide out by -5. So 375 divided by 5 is 75, so that's positive. Okay. So we want to solve this quadratic. Let's check to see if it's factorable. All right, so if it's factorable, 1 times 75 is 75. Let's look at the factors of 75. So let's see, that would be 3 and 25 and 5 and 15. All right, so they have to multiply to give positive 75, and they have to add to give negative 20. So if I put negatives on these two, they're going to add to give negative 20, and they're going to multiply to give 75. So I am factorable, so that's t, 2 negatives. All right, so now I want to set these equal to 0. So t minus 5 is equal to 0. And t minus 15 is equal to 0 would cause this to be a true statement. So I have a true statement when t is 5, when t is 15. Okay, so over here, when t is 5 and 15, I'm at 375. And that is my solution. Okay, so that's the end of this lesson. You should be ready to work the homework problems now. And remember, you can always go back and listen to these videos any number of times that's necessary.